So welcome to today's session. And in today's session, we will be discussing the aerodynamics questions from GATE 2014 paper, right? So the marks distribution looks something like this. You have around three questions that are of 1 mark and two questions of two mark questions which are 5 in number. So totally around 13 marks from the aerodynamics portion. The streamlines of a potential line vortex in concentric circles with respect to the vortex center are shown in the figure. Velocity along these streamlines outside the core of the vortex can be written as v theta equals gamma by 2 pi r. The strength of the vortex is gamma by 2 pi r is in the radial direction. Value of circulation along the curve shown in the figure. So this is a velocity field which is formed by a vortex with velocity given by gamma by 2 pi r. And they have told us it's a potential vortex, which means that it is irrotational everywhere except the origin. So irrotational except at the origin, right, at r equals 0. So they're asking us what is the circulation in the curve ABCD as shown in the figure. Now, here we don't have to do any calculations. We can clearly see that the curve ABCD does not involve the origin. So any point that you take inside this curve is basically the velocity, um, the vorticity is basically 0 here. So del cross V is 0 on any point that you take inside this curve because inside the curve ABCD because it's a potential line vortex, and the potential line vortex are rotational only at the origin. Since vorticity is 0 everywhere, that basically means the circulation is also 0 everywhere inside this curve. Option D is the right answer. Right. To observe a separated flow in a unsteady separated flow in a diverging channel, bubbles are injected at each 10 meters a millisecond interval at point A as shown in the figure. These bubbles act as a tracer particle and follow the flow faithfully. The curved line AB shown at any instant represents. So they're telling you it's an unsteady separated kind of flow field in a diverging channel. And some bubbles are being injected at some point A, and the bubbles basically follow the flow. Um, uh, the bubble acts as tracer particle and follow the flow faithfully. The curved line AB shown at any instant represents. So what does this curve AB represent is the question. So is streamline, straight line, path line, streamlines and path line, only path line, or only straight line? So if you look at what these points represent, so these are nothing but the location of bubbles that have been injected through point A. So basically, these are nothing but um, the streak lines of all the fluid particles that have once passed through this point A. So so in this case, the correct answer here is it's only a straight line, and it cannot be a streamline or a path line because here if it's not, and it's an unsteady flow, so you cannot really say that streamlines, straight lines, and path lines are the same. And also, um, here when you're injecting the bubble through point A, it's not that we are actually tracking a fluid particle all the way in its journey. You're just tracking the different bubbles that have been injected through point A. So it's basically like the location of all the fluid particles that have once passed through point A. So you're not tracking one particle, you're just tracking a bunch of particles and freezing the time interval. Right. So these are nothing but straight lines, and the correct option here is option D. Uh, is when circulation is not zero, in scenario it will not zero. In let's say if my velocity is in such a way that it is not a potential kind of flow field anywhere, like even inside the circulation, even inside the curve ABCD, if my del cross B is not zero, then you would have to actually do the line integration, that is integral V dot ds and figure out what is the circulation. Since it is potential flow everywhere, that is a rotational flow everywhere inside ABCD, this automatically becomes zero. All right. Look at this problem. For a steady incompressible two-dimensional flow field represented in Cartesian coordinates, a student correctly writes the equation of path line of any arbitrary particles as dx by dt equals ax, dy by dt equals by, where a and b are constants. So it's a steady flow, an incompressible flow field, which is represented in the Cartesian coordinates. So student basically writes the path line of any particles as dx by dt equals ax and dy by dt equals by. Right? Where a and b are some constants. A is 5, and they are asking us to find b. So when they say dx by dt equals ax, your dx by dt is nothing but your x direction velocity. Since the flow is steady, so there are no other unsteady components to it. So your dx by dt actually represents your x direction velocity in the Cartesian coordinates, and your dy by dt represents your y direction velocity in the Cartesian coordinates. And the flow is steady and incompressible. So if you were to take the mass continuity equation for a steady incompressible flow field, it looks something, and that in 2 dimensions, it looks something like this: dx by d dou u by dou x plus y by dou y equals 0. U equals dou u by dou x, dou u by dou x is nothing but a, and dou v by dou y is nothing but b. Equating this to 0, you get b equals negative of a, and a is nothing but 5, so b is minus 5. This is how you, it's a very easy problem. So you solve it. Yeah, any questions? Let's look at this problem. Figure A to D below show 4 objects. Dimensions and surface conditions of the objects are shown in the respective figures. All 4 objects are placed independently in a steady uniform flow of the same velocity. Um, um, uh, Same velocity and direction of the flow is from left to right as shown in the figure. The flow field can be considered 2D, viscous, and incompressible. The following statements are made regarding the drag of these objects. So basically, they have 4 different objects, one which is a smooth cylinder of diameter C, one is a smooth airfoil of diameter of the maximum frontal area to be around C. Other is a rough surface which of airfoil with the same frontal area, and then a rough cylinder with diameter C. They're asking which of the following statements regarding the drag are correct. So they're saying a drag of object A is more than that of D, drag of object A is less than that of D, and so on. So we just need to figure out which is the right set of statements. All right. Let's look at first statement. Drag of object A is more than drag of object D. So A is a smooth cylinder, D is a rough cylinder, which is true because cylinder is a bluff body. So more than the skin friction drag, you should be worried about the pressure drag. So the flow separation induced drag. So here in a smooth cylinder, what happens is that your flow will separate very, very easily. Now, because your boundary layer does not have too much energy, your flow will easily separate, all right, and create a lot of drag. While in case of a rough cylinder, what will happen is that because of these spikes, your flow will have a tendency to become turbulent, and turbulent flow will be more energetic, and the flow will remain attached for a little more longer along the surface of the cylinder. So hence, your smooth cylinder will create a higher pressure drag, while your rough cylinder, because of the roughness, though the skin friction is a little will also increase, but in a bluff body like cylinder, the pressure drag is more of concern than skin friction. The first option is right. Drag of object A is less than drag of object D. No, that is not true because we have already established that drag of object A is higher. Let's see, drag of object B is more than drag of object C. Drag of object B is more than drag of object C. This is not true because you have a smooth airfoil and a rough airfoil. So in an airfoil, which is a streamlined body, your pressure drag is quite less because your flow will remain attached for quite some distance. So the major factor contributing to the drag of a airfoil is the skin friction. So when you take a smooth airfoil, the skin friction is quite less because the surface is smooth. But in a rough surface, though you will delay the flow separation, but the skin friction will be largely enhanced. And the pressure drag is not much of a huge criterion for the airfoil per se. So in this case, your rough surface of airfoil will have higher drag as compared to the smooth surface of your airfoil. So this statement is again wrong. Your drag of object B will not be more, it will be less than that of this. Look at the fourth statement. Drag of object C is more than drag of object B, which is true. We just established that. The rough airfoil will have more drag than the smooth airfoil. Drag of object A is more than the drag of object B. So drag of object A is more than drag of object B, which is absolutely true because it's a block body, so it will be a lot of pressure drag. While this is a smooth airfoil, so it has less skin friction, and also since it is streamlined, it has less pressure drag as well. This is also a correct statement. So we have 1, 4, and 5 which are correct. So option C is the right answer over here. All right. Questions here. Let's look at this question. A student can measure free stream velocity of a low speed wind tunnel using. So they're asking what are the things that are required to measure the free stream velocity in a low speed wind tunnel. A pitot tube alone aligned in the flow direction. So basically, if I take just a pitot tube and align it to the flow direction, can I measure the free stream? So pitot tube is basically, so there are two components, right? We have the pitot tube and then the static probe. So pitot tube will measure the stagnation pressure, and the static probes, on the surface will basically measure this, the 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 pitot tube will measure the stagnation pressure, and then the static probes will measure the static pressure. And with that, you can calculate the dynamic pressure and correspondingly the velocity. In this case, if I'm using only a pitot tube and not a static probe, then I really can't measure the free stream velocity, right? So option 1 is not true. A pitot tube aligned with the flow direction with static pressure measurement at an appropriate position on a tunnel wall. So here they're saying you're having a pitot tube, but then the static pressure probe is kept at some position in the tunnel wall. So that will work because your idea is to measure the free stream velocity. So so the velocity everywhere is the same. So free stream velocity will be constant everywhere, right? So even if I have a pitot tube and then my static probe is somewhere else, and but as long as it is in contact with the free stream air, it can still pick up what is the uh, static pressure of my free stream air. And with this combination, I can find what is my V infinity. Right? Let's look at the third option. Pitot tube aligned with the flow direction along with the barometric pressure reading of the outside ambient. So this probably won't work because your pitot tube will give you the P naught, but the barometer pressure reading of the outside ambient. So outside ambient pressure, if you're measuring and then taking that to be your P infinity, it won't work because your outside air is static air, right? That will give you the atmospheric pressure, but you need the static pressure of your moving air, which your barometric pressure reading won't give you. So you will end up with the wrong value of velocity. All right. So this also won't work. Last is pitot static tube around along the flow direction. Pitot static tube is basically the static probes lie on the pitot tube itself. And this will also work out, right? So you have the pitot tube giving you the P naught and then the static probe picking up the static pressure. And with that, you can get the V infinity. This is also a correct option. The right option here is option C. You have your 2 and 4, which are the right options. All right. Look at the next problem. The induced velocity W at a point Z1 along the lifting line can be calculated using the formula W of Z1 minus 1 by 4 pi minus S2 plus S d gamma by dz into 1 by z minus z1 given gamma by gamma naught square plus z square by 2s by square equals 1 by gamma naught and s are given in the figure below. For the above semi-elliptical distribution of circulation, the downward velocity at any point z1 for the symmetric flight can be obtained as so they have a symmetric elliptical distribution, which we know, which we've already studied from Francis line theory. And they're telling us that the downward velocity at any point z1, so z1, any point z1 that from the origin, if you take the downward velocity can be written as gamma naught by 4 uh, pi s into uh, pi plus z into I, z1 into I. All right. And where I is, an integral they have given over here. Z1 in integral minus S2 plus S dz by S square minus Z square into Z minus Z square. All right. And which of the following option is correct if the induced drag is di given as um, um, uh, given that this integral is nothing but pi s by 2. All right. So here they're asking you what is I and di. What is this I inside this induced drag expression, and what is your induced drag for that matter. So we have already studied Prandtl Lipman theory, so we know what these things are already. What is my induced velocity, and so on and so forth. My induced velocity is nothing but for an elliptical lift distribution is nothing. It's a constant value, and it is nothing but gamma naught by 2b. All right. Where b is nothing but the span of the wing. All right. And in this question, you can see the span is nothing but 2 times s. You have s as a half span, another s as the other half span. So your b is nothing but 2s in this case. All right. So you have gamma naught by 2 into 2s. So your w is nothing but gamma naught by 4s. Right. So which basically means that my I should be equals to, so if only the I is 0 over here, I'll get omega equals, and this pi and pi would get cancelled. My omega is gamma naught by 4s. All right. So hence for this elliptical lift distribution, it basically means that my I is nothing but 0. Right. Only then I'll get my whatever we calculated for according to Prandtl plan theory for elliptical distribution. Your induced velocity will basically match out. All right. And next they're asking us what is the induced drag. All right. So the induced drag, di is nothing but your induced drag coefficient CDI into half rho infinity v infinity square times the surface area of the wing. Right. And you know that the induced drag coefficient, according to Prandtl line theory for elliptical lift distribution, is given by CL square by pi AR, right? And into half to infinity infinity square times S, right? And we know that the CL for elliptical lift distribution can be written in terms of the circulation as gamma naught into B into pi by 2 V infinity S. So all these are basically coming from Prandtl theory. You don't have to derive anything. Everything is already derived. right? You don't have to do any kind of derivation. You can just use the formulas directly. So substituting CL from here, I can write this as gamma naught square B square into pi divided by 4 B infinity square into S square into 1 by pi AR. Pi AR is nothing but uh, B square by S, and then you have half rho infinity V infinity square times S. So you have, this um, S cancel, this S and this cancels, B square cancels, pi and pi would get cancelled. So ultimately, this will turn out to be um, around a value of uh, gamma naught square pi rho by 8. Here, V infinity will also get cancelled, right? The induced drag is nothing but gamma naught square pi rho by uh, 8, all right? So which is nothing but if I look at option C, I have I equals 0, di equals gamma naught pi rho by 8. So option C is the correct answer over here. All right. Any questions on this? Let's look at this problem. Two overflowing water reservoirs are connected with a 100-meter long pipe of circular cross section of radius 0.02 meters, such that the height difference remains constant as shown in the figure below. The centerline velocity in the pipe is, so there are two reservoirs which are they're overflowing reservoirs. They're connected by a pipe which is 100 meters long. So this reservoir will fill in water which passes through this pipe and then fill this reservoir, and if it overflows, it goes out from this pipe. And the uh, the height of this height of water level in this reservoir and this reservoir are the difference in their height remains a constant, which is called h. The velocity profile inside the pipe over the entire length is the Poiseuille, plane Poiseuille, the Hagen-Poiseuille distribution. All right, minus r squared by 4 nu into dp by dx into 1 minus small r squared by capital R squared, where dp by dx is a constant pressure gradient along the pipe length. So this is the velocity profile that is inside the pipe, and then dp by dx is a constant pressure gradient, etc. Now, given the data that water has a density of 1000 and viscosity, kinematic viscosity, which is nothing but nu of 10 power minus 6, and acceleration due to gravity g is 10 meter per second square. If all laws except the frictional losses of the pipe wall are neglected, what is the value of h in meters? So they're basically asking us to consider the effects of friction and calculate what is this h value. And initially, this might seem like a very complicated problem, but let's just break it down into one by one. So the main reason why the height of the reservoir, doesn't reach as much is basically because of all the frictional losses inside the pipe. So the frictional losses inside the pipe will cause some kind of a pressure drop. Plus, at the same time, it will cause some kind of a height difference as well, a potential height difference because of friction. And from um, uh, you know the frictional calculations, we know that the from any standard textbooks you can get this. The height loss, or what we call as a head loss due to friction, is nothing but 2 into shear stress into length divided by rho into g into r. So the shear stress of the wall times the length by density into acceleration due to gravity times the radius for the pipe will basically give you what is the height loss, that the frictional loss that is being created. So I know what is the length of the pipe. I know what is density G and R. Now only thing which I need to find what is the wall shear stress in the pipe, and I can calculate what is the head loss, and that will basically give me this H. So this H is nothing but how much amount of height is lost because of friction, which is nothing but your head loss due to friction. All right. So let's go ahead and find what is my tau W now. So first let's look at U. U is nothing but minus I'll just write here. So U is nothing but minus R square by 4 mu dP by dx into 1 minus small r square by capital R square, right? And they're telling you that the x is measured with respect uh, the center line velocity in the pipe is 10 meters per second. So which means that at r equals 0, my u is nothing but 10, right? If I substitute that here, so when my r equals 0, this goes to 0, you have 10 equals minus capital R square by 4 mu into dP by dx. All right. So I can replace this minus R square by 4 mu dP by dx with 10. So my velocity u will basically look like this. N into 1 minus small r square by capital R square. All right. And my tau will be nothing but mu into dou u by dou r. Right. So mu into 10 into uh, minus 2r by capital R square. And here, since I'm finding the friction of the wall, my r equals capital R. My tau will be nothing but minus mu into 10 into 2 by this r and this r would cancel if my r equals capital R. So you have 2 by r. All right. And my frictional head loss due to friction is nothing but 2 uh, 2 tau L by rho gr. So 2 into tau L by rho gr. And let's just substitute the values. You can ignore the negative sign. And that is this mainly coming in because it's showing you that it's a force in the opposite direction. So while calculating the shear stress, while calculating the HF, you just need to only use the magnitude of this, right? So 2 into mu into 10 into 2 by r, and the radius here is 0.02 as given on the question. So the radius is 0.02, right? And then the length is 100. Right? The density of water is 1000. Acceleration due to gravity is 10. And then my r is 0.02 meters. Right, and mu is nothing but so mu by rho is the kinematic viscosity, which they have given it as 10 power minus 6. Right. So if you do all these calculations, you will end up with an HF value of 1 meters. Right. So basically telling you that this height difference is nothing but 1 meters. Right. So this is how you solve this problem. Yeah. Any questions on this? Yep. Any questions?
Uh, Sir, dou p by dou x, u equals to minus r square by 4 mu dou p by dou x. Where is the dou p by dou x? That means you have taken it 1.
No, so since they've given us a center line velocity, I can just, if I substitute r equals 0, I'll get minus r square by 4 mu into dou p by dou x equals 10. So then whatever this guy is, I can just take it as 10, and then my u becomes 10 into 1 minus capital small r square by capital R square, right? The questions. Okay. So that's all we have for today's session. Yeah, thanks for joining, guys, and all the best for your GATE exam, right?